We get to finish our thermo unit today. So hopefully you're caught up on all the stuff. I wore a chemistry shirt for this video and I forgot. Yay!
How many chemistry shirts do you have?
Like a lot. Like a whole lot of them. This is awesome. Okay. Ta-da! I'm a chemistry teacher now. Anyway, so let's jump into the last couple topics. Okay, entropy is going to be our first focus. Entropy, by definition, is it's a measure of disorder, and it turns out that the universe that we live in favors entropy. Everything that's happening around us spontaneously becomes more disordered. Some of the simple examples you can think of to support this idea is never, unless you have parents that just love you so much, have you ever come home from school, walked into your bedroom, and it's suddenly completely clean all by itself?
That's happening.
Instead, what does your room do after you clean it?
Every Tuesdays and Thursdays.
It gets messy all by itself. That's entropy. The universe pushes towards entropy, disorder. Another example is never has your mommy or your daddy who does your laundry thrown all the clothes in the dryer, let it go through the drying cycle, open it up, and they're sitting in there folded. That doesn't happen because when the universe is just getting to do things spontaneously, entropy is going to increase disorder. The variable that we use when looking at entropy is S. And you just need to understand that a positive S is going to signify an increase in entropy. So the second law of thermodynamics is the connection between the universe and entropy, just stating that anything spontaneous will increase it. There's a synonymous term with spontaneous, and that is thermodynamically favored. They get used interchangeably, so you'll want to make sure that you understand that they mean the same thing. If a reaction is thermodynamically favored, that means it's supporting the laws of thermodynamics. Therefore, it is supporting spontaneity, an increase in entropy. Now, the good news about S, our new variable, is that most of the time you can just use Big Mama to solve. Actually, you can for the other thing we're going to look at today. What's interesting about your AP sheet is when you get it on your test, Big Mama is written 3 times in a row, right over each other. One for H, one for S, and one for G, which we'll get to in a little bit. So it is possibly the most used equation on the AP since it's there 3 times. So make sure that you are comfortable using Big Mama.
And there's 9 degenerates in the hallway.
If there's 10, I do something, not 9. Okay. So you can see Big Mama hanging out down there. Let's go ahead and prove that she works for S. So here's a problem. Oh, there's a typo here. Fix it. For some reason, I got the right table, but then I grabbed a question that asked about delta H. Everything is perfect on this slide, except for instead of delta H, the question should refer to delta S. We're calculating entropy right now. Yes, ma'am.
Your slides are.
It's too late. This is why we tackle all. I can't do anything about. I mean, they're there. Y'all saw the slides, right? Okay. So one thing I'd want to point out real quick. All right. You see the little circles that look like degree signs? It's called a knock sign. What that's referring to or letting you know is that this is under standard temperature and pressure, all right, which is 298 Kelvin and 1 atmosphere. I've told you before that 298 Kelvin is always going to be, well, not always for gases, but is generally your standard temperature. The very first lecture we ever had together in this class, I opened up with 25 degrees Celsius as standard temperature, and you should just always know that. Hopefully you remember that. But anyways, 298 Kelvin is what that knock is telling you, which is important since one of our equations we're going to do soon is temperature dependent. The other thing I want to point out is, what do you notice about the values of enthalpy connected, entropy, sorry, ma'am, I don't need to do that. The values of entropy connected to free elements. They're not zeros. All right. So if you look, all right, they're not zeros. So it doesn't zero out in this regard. For H and G, it does, just like we previously learned. So let's go ahead and run Big Mama real quick, just to prove that it works. We've got our equation down there. It's going to be sum of products minus sum of reactants. So let's start off with the fact that we only have one aluminum chloride. All right, and we're going to be multiplying that. Then the AlCl3S, which is 111, minus the sum of the reactants, starting with my 1 aluminum, which based on entropy is going to be multiplying times 28. Adding that to our 3 halves chlorine, which is going to be multiplying by 223. I'll give you a moment to try to solve. Where? Oh, yeah, it's sum of. It means the sum of.
What's are we basing this on?
I get negative 250. Smallest one. We all right?
Yeah.
All right, so that was just Big Mama being used for entropy instead of enthalpy. So hopefully it feels the same. Now, so that's the good news. Here's the bad news.
Okay, talk about it. Is it 250 because of the 260?
Yeah. Hey, what did you got? 251? Okay. 250. While Big Mama is certainly given to you on your AP sheet, there's 2 equations here that are not, that you'll need to know. So you're going to add this to your memorization list, along with, of course, things like your solubility rules and strong and weak acid bases, all that stuff that's still on the edge of your brain, right? So it's the very top and very bottom ones that you're going to want memorized. One of them is the way that you find the change in S of the surroundings. All right. What we looked at a moment ago was the entropy of the reaction. This would look at the the entropy of the items that are not the reaction. And this is the equation that is not given to you on the AP sheet.
So then, well, how would you know which ones aren't used to do reaction?
No, it's saying if the question is asking for the surroundings instead of the reaction, you would use this equation. It would pinpoint that that idea.
Oh, we have to memorize this?
Yeah, the very top one and the very bottom one. And the very bottom one is easy. In order to find the total entropy of the universe, all right, you would need to be looking at both the system and the surroundings.
The whole universe?
Of the universe after the reaction that you're looking at is finished, because you can see how it changes overall.
How does eating bananas that are brown?
All right, so with these new 2 equations in front of you, let's look at a problem that will incorporate everything. All right, so here's a fun little table. dealing with the reaction of nitrogen and hydrogen to produce ammonia. All right. So let's just go through the questions. Question 1, calculate the change of entropy of the system. That's the first thing that we did. All right. Entropy of the system is big mama. So we can do that. Start looking at my reaction. So we've got 2 NH3s. So we've got, remember, products first. So we're going to go 2 with the NH3 value of 193. And we're going to subtract the reactants, starting with my 1N2 with an entropy value of 192. Being added to 3 hydrogens with an entropy value of 131.
It's cool. It's like you're checking on, like on us. Like you're checking on us. When you do that, that's how
I get negative 199, do you?
Yes.
So that'd be negative 199 joules per mole Kelvin. All right, and that is my entropy of the system, just like it wanted us to find. So far, nothing. That was just Big Mama. All right, because that you use Big Mama when finding the entropy of the reaction. All right, but let's go to B now. B says calculate the change of entropy of the surroundings. All right, the surroundings. Look back to the previous slide. That's one of your new equations. All right. In order to do it, it says that we need to go the change in H, all right, divided by the temperature, change of H of the system. Now, I don't have the change of H of the system yet, but we've got values to find change in H. That's still just Big Mama. We already learned how to do that. All right, so we can find my delta enthalpy here by going Big Mama again. Now, this one's actually really nice, though, because when we look at our reactants, it's going to be 2 times negative 46.1. And then what's true about the reactants? They're all 0. All right, so I'm going to get a value of negative 92.2. Kilojoules.
How do we know if it's H or S? Real talk.
Well, I mean, I ran S based off S numbers, and then I ran H based off H numbers.
Oh. And so S versus what?
Sorry?
What's S cis
That's going to be the entropy of the system.
and H cis?
It's the enthalpy of the system.
Oh, okay. Thank you very much.
All right? So we've got an answer here, but it's not right. Look here. I want you to look back at the equation. Sorry, wait. All we found is, we haven't finished. Here, let me rephrase the way I want to say this to you. Look back at the equation that we're using to answer question B. Remember, question B wants us to find the entropy of the surroundings. What?
Question B.
You said question.
You said question.
If you go back to the previous slide, you will see that the equation has something interesting before the delta H. Look back at the equation. What does it have? It's got a negative symbol. It says that to find the entropy of the surroundings, it's going to be the negative of the delta H.
So it's
In
gonna be
other
positive.
words, you flip the sign. All right, when using this equation, whatever you find for delta H using Big Mama from what we previously did, you then flip this sign before you divide by temperature. So I have now flipped the sign by doing a negative times a negative, basically.
Period. No.
All right, now it says that we want to divide it by temperature, and here's where I was going a moment ago. I want you to compare our entropy to our enthalpy values that we've calculated so far. What about them makes them impossible to compare?
They're different.
They're different units, all right? Those are called units. Yeah, they're different units. So before I divide by temperature, because that's what we're going to do, right? You keep looking back at how to find the enthalpy of the surroundings. It tells you it's negative delta H divided by temperature. But what I want to fix real quick is the fact that comparatively, they're in different units, all right? So I can change this to joules real easy, right? We just slide that decimal to the right 3 times.
Joules. RIP.
All right, so if I do that, it'll become 92200 joules per mole.
Whoa. Did we just multiply by 1,000?
So there's the better value. Are we still okay? Because now they're directly comparable. Yes?
Do we have to show that it's positive outside?
At this step, not necessarily, because we haven't answered a question they've asked us. So Carolyn pointed out that this is more correct when looking at delta H by showing that it's positive, but we're at an intermediate step. We haven't answered anything yet. Because our next step is to divide by temperature.
Wait, sorry, are we supposed to put a positive?
At this step, you don't have to.
Okay.
All right, divided by what is the temperature?
1.
298.
What?
Where?
No. Oh, where y'all seeing
That knock symbol is letting you know that everything here is standard and you are responsible to know that number.
Is it given to us on the AP exam?
It might be actually.
If I stand correct.
Wait, so what is this then?
So it's this is the final item that we're having to do to answer part B.
Oh,
All right, because it's supposed to be this divided by this.
So the answer is...
so when did we answer for A?
Yeah.
Wait, are we still not done with part A?
Okay.
No, part A, that's the answer to part A. We haven't found the answer to part B yet.
Oh,
All right, and I'm ending up with, you get 309?
yeah.
298 is standard temperature, and anytime you see those symbols right there, it means everything is happening at that temperature.
Oh, so if that symbol's not there, the temperature is different.
Right, exactly right. Or is being salted.
Okay, I'm on the same page.
All right? So here we go. We found it. We answered part B by simply we ran the equation, right? The equation said to find that, you need to go the negative change in H divided by temperature. So we found the change in H, we switched the sign, converted it just so the units match, and divided by the temperature.
All right, the next
Part C says calculate, it's the answer to B. Part C says calculate the change of entropy of the universe. Again, go back to the previous slide. What do we do to find that?
We are going to use Big Mama. No, you're going to add both of them.
Just add them up. So 309 plus negative 199, all right, is going to give you,
110. No, it's not.
yeah, it is.
Oh, it is?
You nailed it.
Did I really? Ow, no, I didn't. Don't mind.
It's 110.
Oh, it is 110. Real talk.
So, you find the 110, and that's great and all, but look at question D. Question D says, is the reaction spontaneous? Is it?
Yes.
Why yes? Because the answer you got is positive. Right? So remember the way to draw conclusions here. If S is positive, then it is spontaneous. And if it's spontaneous, it's thermodynamically favored.
Wow, that's a nice word to call it, just for being a positive. Is it negative? Like, is it malicious?
I think they call it a
Negative?
synquiz. It's weird.
That's good. Positive is positive. Sorry, I actually started. Sorry, choking on plastic.
Yes?
You're saying the universe one is spontaneous, right? Because the one for the list is negative, right?
Right.
So would that make it not?
The over...
Water. It's like sticking to my tonsil. Tonsilla? Is it tonsilla? Yeah, anatomy and phys is not my thing. I thought a uvula was a uvula.
You're right. It's pinpointing reaction in that final question, isn't it?
Keep coming at me for that. It's Hyundai. The U is not silent.
Like, is there like a counter? Because it was
Entropy's always winning.
Is there like somebody counting?
So what would happen if
Yeah, I don't like the last way that it words it there at the end while having you find both. One of the things that it won't have you do is find two different S values in the same question like this one did. All right, this problem is just pulled from a textbook, not an AP exam. So that would be the silver lining of that possible confusion.
what was the confusion?
There's two different S values to
Oh, okay.
compare, one positive, one negative. If you walk into the test knowing that a positive entropy is thermodynamically favored, you will get all questions correct in regards to that concept. Speaking of concept and conceptual, here's a non-mathematical way to look at this idea. This is what some of y'all have been struggling with on the enthalpy, I've noticed, but, sorry?
Every time ice melts, can you play the song Ice Melts?
Dude, I'm not going to finish this lecture. You're the reason I eat less. Come on. You're the reason. I don't know. That sounded weird. That didn't come out that way. You're the reason my lunch period is shorter.
Are you blaming
Cheetos.
your eating disorder on him?
You're the reason I'm anorexic. Okay.
Oh my gosh, I found out.
Oh my gosh. All right. General ways to increase entropy conceptually. Anytime the phase change is going towards gas, entropy is going to go up. Think about it. That makes sense because by definition, the phase of solid has more order, right? So when you go to gas and they're bouncing all over the place, well, that's wilder. That's more unpredictable. That's going to have more entropy and disorder. Anytime a solution is formed, all right, dissolving something in something else, you're increasing the entropy, all right? I mean, if you think about it, you're breaking bonds and letting particles move around more freely. Anytime the volume's increased in a gaseous system, if you have a small balloon where the particles are moving around, they have entropy because they're moving around wildly, but make the balloon bigger and now they can move around even more in even a higher degree of disorder. And then finally it says temperature increased, but there is something here I need you to add to your notes. Add this. Where you put temperature increased, you need to write single substance in parentheses because that one can be misleading. What this is supposed to refer to is the idea that if you have a piece of metal and you just start heating it, then you're going to increase its entropy, all right, by definition. Increasing the temperature of a single sample will increase the entropy. However, if you have a reaction that produces a solid as a product, and you increase the temperature, that's going to make it increase the solid faster, which is decreasing entropy by going against the phase direction of gas. So you've got to be careful using temperature as a solitary guide.
Can you go over the example we used
For the what?
the example we used to verify what the solution form is?
Oh, for solution form, it's just if you're dissolving a solute in a solvent. When the solute dissolves, instead of it being bonded, now it's unbonded, that'll have more entropy with the freedom of motion.
So the temperature increases only for
A singular substance, right? And here's another thing that I've seen trick questions that I don't want you to mess with. Carolyn, stop it. students start to think that only phase changes can indicate an entropy change. No. If I have a piece of metal and I'm heating it up and it stays solid, the entropy is increasing just by adding the heat to it. A phase change is not required. All right. Now, a phase change will certainly represent one, but it's not necessary when you're connecting temperature to this idea. We're going to get Aspen in play because it's fun. So let's do some practice and see if we understand just basically what we are talking about here. All right, so we're looking for an increase or decrease in entropy. You know the order I'm going in, so just be prepared with an answer if you get called on, please. So let's head over to cluster 3, seat 1. 3-1, what do you think about ice melting? Will that increase or decrease entropy? She says increase. Do you agree?
Yes.
I agree. It's going towards a solid to a liquid is towards the gas phase. That will increase entropy. Let's go to cluster 4, seat 5, Aspen. What do you think about a precipitate forming?
It's a decrease
Why?
because the solid is more.
Decrease. That's a solid. She formed a solid, therefore decrease entropy. What just happened?
What cluster is this?
1.
You didn't say one.
I did. Oh, no, but I missed, so it went to Aspen.
Okay.
Can I have Aspen?
You look like you just woke up with a, I was going to say pneumonia.
Confused. So I was like, oh, cool.
What cluster is this? Where am I?
Wait, what's the solution form though?
What?
A solution?
What?
This is focusing on the formation of that precipitate, nothing else in the equation.
I was only.
All right, a solid dissolves in water. Let's go to cluster 3, seat 1.
What?
Okay.
I didn't even hear your question.
A solid dissolves in water.
Solid dissolves in water.
Increase or decrease entropy?
Increase.
That's correct, because you're making a solution. We doing okay?
Wait, apparently, what was the precipitate?
That was decrease because you're forming a solid.
Can we learn about osmosis?
I was there.
I got it. We can watch osmosis.
Hey, more practice. Hey, this time, instead of telling me increase or decrease, I want you to tell me if S would be positive or negative. Would S be positive or negative? Come up with your answers. Let's go. Shush your mouth. Let's go to...
See,
Shut your ugly mouth. Go to cluster 5, seat 5, Aspen. Would the first reaction have a positive or negative S?
How do you figure that out?
Look at the phase change. Look at the phase change.
Look at the face change.
Oh, solid.
It would be negative, all right, because it's going towards solid. That's a decrease. That'll be a negative S.
Wait, where?
What?
Sometimes I know, right?
Zeta pi? That's Greek. You're a 6'2".
Wait, your turn.
I asked first.
You're 6'2". All right, let's go to cluster 2, seat 6, Aspen. What did you get for the second reaction?
Oh, wow. For real.
Hang on. Shh.
Wait a second.
Who's here?
No. But there's nobody there. Oh.
Got him.
Do we have to rotate Aspen?
Yeah. You can't. I don't know.
All right, so here, quiet, because this one's harder. What is the difference between the reactants and the product?
There's no.
They're both gases, but what's the chemical difference? We broke a bond, all right? So what do you think is going to be true if you break the bonds of something? Do you think that's going to make things more disordered? Yes, it will. All right, it'll make things more disordered, right? If I'm here and me and Alyssa are bonded together, all right, we can't cause a lot of havoc and craziness. But man, if we detach, I'll rob a bank.
That's another moment.
You're like, so this one is like that.
Yes, positive S. Let's do the last one. Cluster 2, seat 2. Hey, Tutu, what'd you get for the last one there?
Wait, so negative?
She says negative. I agree. We started with 9 moles of gas and ended with only 4 moles of gas. All right? Therefore, it's going in a phase change towards solid. That'll be a negative S. Yes?
Okay, you said if you're like unbound or whatever, it causes more destruction. Why would that?
It causes more disorder.
Whatever.
Because now I can go wherever I want instead of being bonded to.
Why is that positive?
You wish it could be bonded.
Because increasing disorder
You're like, I'm
increases S. Isaac, she was asking me. Increasing disorder increases S. Because S is disorder. The whole system's out of order.
So you
Okay.
said the last one is positive?
Can you not be
okay.
rude to Isaac?
No, the last one's negative.
Just think of human examples.
Help me! Thank you.
Oh, I'm sorry. Maybe
Wait, why
you have more.
All right, so let's go to the last topic of the unit. That's exciting.
It's Gibbs.
Oh, Gibbs load up. I'm an AP Chem teacher.
All right, so Gibbs free energy is gonna be G. And again, G is one of the 3 big mamas that you're gonna see on your AP sheet, stacked right on top of each other. So again, if you know how to use big mama, you can solve half of all the G problems. That should be good news for you. All right? Now, when can you not use big mama? What about the other half? Well, it turns out that big mama only works in standard conditions for G, which means the moment it's not standard, the moment it's not 298 Kelvin, then you've got to use a different equation. Now, this last equation is given to you. It's on the sheet also. So you don't have to memorize it, all right? If you did have to memorize it, then I'd call y'all all ghetto homies.
That's kidding.
Yeah, you are. No. Y'all know who the ghettoest homie is? Cluster 5. I'm just kidding. I'm not gonna do it. Anyways, now I have to know. Okay. Only I know the ghetto homie.
5-4.
Now, the reason I put ghetto homies up there is not for you. When I took my composite exam, I'm certified to teach any science in the state. But in order to get that certification, I had to take a ridiculous test. And on that test, there's no formula chart. None.
You passed?
It covers biochem, physics, astronomy, and earth science.
Wait, this was to do what?
This was to have the certification I have to teach any science.
you're
So anyway, so
You didn't even get periodic.
when I was studying for that ridiculousness, I had to come up with mnemonics to memorize over 100 equations. This was ghetto homies. I just wanted to share it with you.
Wait,
Um,
that's crazy.
Still memorize some of them? What's Avogadro's number?
6.3333. Shoot, I got it wrong.
Wait, I don't.
You're gonna ask me the easiest one? Okay, here we go. No, we don't have time for this. Anyway, so let's take a look at some free energy stuff.
I don't understand how ghetto.
I don't understand where you got to get off on the
The
triangle.
whole thing.
G8. Did you get a 100 on the test?
It's
Why
not
is the
hard.
triangle G equals triangle H minus T triangle?
Look, if you don't get it, you're not my people.
Arguable.
Okay.
You're not
Now, I want to point out that the sign is just as important now as it's been in everything that we've talked about in this unit. Because we know that the sign of H tells you exo-endo. We know the sign of S tells you thermodynamically favored or not spontaneous. The sign of G tells you the same thing as the sign of S, but it's the opposite. So, one thing that I do want you to walk into the AP knowing is that a positive S is a positive S is thermodynamically favored, just like a negative G is thermodynamically favored. So what's the relationship mathematically between G and S? Inverse, all right? Inverse. No, not numerically. Not numerically opposite. You don't just get to change the sign. That's not what I'm saying. I'm just saying that if S says that it's thermodynamically favored, then G will say it too, using an opposite general sign. All right?
flipping the sign.
So, again, no, you're not flipping the sign. It's just saying if one is positive, the other is negative, not the numbers being the same.
on.
All right, so let's take a look at what we can do here. I want to point out that this problem is under standard conditions. Therefore, what should we do to solve for G if everything is standard? Just use Big Mama. But I'm going to use Big Mama and Ghetto Homies just so I can prove to you that they give you the same answer. Now, let's go ahead and use Big Mama first. All right, we've got a reaction that should look similar because we used it earlier today. But if I use Big Mama and I start with my products using G, we would start with the fact that we've got one product. All right, aluminum chloride giving me a negative 629 value. All right, and what do you notice about the reactants in this problem?
0.
Yeah, G is like H. Free elements are 0. So look here, we've got negative 629 is my answer.
God bless America.
Yeah.
Bless you.
Now, we could be done and move on to the next one. But again, I want to prove ghetto homies to you because they're just so good.
Oh, it's like a generates in the hallway.
So we know that my ghetto homies equation is my change in G, all right, is the change in S minus T change in S.
Oh, okay, we're on the same page about ghetto homies now.
Good. Ghetto homies. All right.
I think the hot sauce.
So now we can do some plug and chug. Now, what I see here is that I can find these other values, right? So what we'll want to do is start by finding delta H using, again, hooray, Big Mama. So using delta H, I can see that I've got one aluminum chloride with an H value of negative 704. And again, as we expect H to do, all the reactants are zeroed out because they're free elements. So we get an answer of negative 704.
Wait, why did T triangle S disappear?
It hasn't. I'm just solving step by step.
Oh, okay.
Because I need to fill stuff into here. I don't have the numbers yet. I'm going to find them. I just found delta H.
Oh,
Now let's
okay.
find delta S.
Okay.
All right? So let's go ahead and find delta S now. Entropy. All right? Again, we've got only one of the product, and it's got an S value of 111. Oh, wait, we don't need to do this. Sorry, I lightened our time. I want you to glance back to our first example from today. Find the S value. We already did this. I used the exact same reaction. What is our change in S? Negative 250. All right, I did this to save time because we can only do Big Mama so many times and have it mean anything to your brain, right? Now, we do have an issue though. Look, we've got everything we need to find delta G. We've got the H, we know the T, it's standard, it's 298, and we've got the S. But what is wrong before we move forward?
The T.
The wrong order.
The KJ, they're not the same. The units aren't the same.
The units aren't the same. We don't have to change the sign. It's only for finding the entropy of the surroundings. All right, that's not happening here. All right, what is happening though is that joules and kilojoules are different. That's always going to happen in these problems. Don't miss it.
So negative 70,400.
All right, so I'm going to change this to kilojoules, and it's going to become negative 0.250. Now we can plug, chug, and smile to find my Gibbs free energy. We're going to take the enthalpy of negative 704, we're ghetto homieing now, minus, we're going to do my temperature of 298 because you see that knock there that makes it standard, all right, times my negative 0.250 entropy. And I'll give you a moment to beat me to the answer. The bell is going to cut me off. You're welcome to stay. I've got 2 more problems to do. I'm sorry? It's just sitting. Oh. All right, do you see how it's practically the same number? All right, do you see how both ways give you the same Gibbs free energy? So that's the idea. What?
I got,
You should get you should get this.
I got 6.
You got it wrong.
I did that
Negative 6.
Okay.
629.
Okay, that's it. That's the right answer. Negative 629.
I got negative 778.
All right, so there's something wrong with your stuff here.
Um,
No, it's just I'm just showing you that they're almost perfect.
Okay.
All right. Help out.
Wait, why did we do it if we could get that answer?
Oh my.
You didn't have to. I was just proving to you that both methods give you the same answer. But on this question, you're not going to have a choice. On this next one, you have to use ghetto homies. Yeah.
Why is temperature 298? Is that
Because in the box, everything that we pulled our numbers from had the knock sign telling me that everything was under standard conditions.
but this is in the different one? Would they give you a temperature or
For what one? For this next one?
again for what?
It depends. It all depends on the way they're doing. Like this next one, temperature is missing. We're going to be solving for it, so it could be anything. So this next problem is a very common way that that the AP likes to ask, because you have to really understand what you're talking about to draw a conclusion from your work.
Why was somebody temperature if there's not?
Well, hang on, because we have to read what the question. I mean, look, it says calculate the temperature. So here's what this wants us to do. It says, shh, y'all's rumblings are too loud. It says calculate the temperature at which the reaction will become thermodynamically favored. So we're looking for a specific temperature, so we're gonna go ghetto homies. Here's the idea about the question, though. It wants to know the temperature at which it will become spontaneous. What do we know about G? What has to be true about delta G, free energy, for it to be spontaneous?
Or negative.
It's got to be negative. So here's what AP wants you to think through. We want to know the moment it becomes spontaneous, which means we want to know the moment that G becomes negative. So here's the way to solve it. Get ghetto homie set up and set G to 0. Because if you know the temperature over here that makes G 0, then you know the exact moment that lowering that temperature will make it negative. Did that make sense? If you have ghetto homies and you make G 0 and you fill in all the information over here to make it equal 0, whatever that temperature is tells you the moment right before it becomes spontaneous. Because the moment G isn't 0, it's negative anything, then it's spontaneous. So by running this data, we can find how G becomes 0, and then we'll have a temperature. So let's do it. All right, so ghetto homies. All right, we need all this information. So I'm going to start by finding my H. All right, looking at my product. Oh, look, it's a 1-to-1-to-1 ratio. There's no coefficients to mess with us. So I'll start with NH4Cl, all right, which is going to be negative 313. All right, and that is the only product minus the reactants. We're looking at the HCl of negative 92.3. All right, plus the other reactant of ammonia hanging out at negative 46.1. All right, if we run that data, I'm going to get a delta H of approximately, if I have not been flipping pages apparently, 175. So this is going to be 175 is what I get to there. All right, and of course that's hanging out in kilojoules. Okay. So now let's find the delta S so we can put him in. All right, running the same type of values. We've got ammonium chloride there hanging out at 193. Oh, I'm sorry, at 95. Minus, let's go over to the reactants. The HCl is 187. Plus the NH3 of 193. And now we're going to get our entropy of approximately 288. Oh, that 175 is negative. Let's say that
I got negative 285.
doesn't look right. Oh, yeah, you're right. It's 285.
Is it not? Is it supposed to be negative? Yeah, because that would be a big negative.
All right, I'm just having trouble reading my writing. In the last class, I was able to calculate these because we weren't this low on time. but my writing is very small. All right. So now I've got both of these values, but look, you know what issue we have. All right. The units for kilojoules to joules is bad. So I'm going to make this 0.285 kilojoules. All right. So that we're able to do a direct comparison. All right. So now here's where we got to think through it. All right. Remember what we wanted to do. To find the moment that it becomes spontaneous, I want G to be 0. All right. I'm going to find that temperature. And now I can input my values. I've got negative 175, all right, hanging out there, minus the temperature. That's what I don't know. All right. We're trying to find T. All right. Times 0.285. Yes, oh God. Miss a negative in one spot and they disappear everywhere.
But I still don't get like why we're trying to find temperature if there's enough.
There's no variables on this thing. I don't understand.
It's letting you know that the H and the S, that these are theirs at the standard pressure. But the G that we're looking for is going to be based off a specific temperature to make it hit 0 so that we know the moment it becomes thermodynamically favored.
Okay.
All right? Because 298 is not going to make it I mean, it will based on the answer that we're going to get, but we don't know that for sure yet.
Cummings, this is not variable.
The T is the variable.
All right, so temperature is what we're solving for. If you do your algebra, all right, Islam, I'm going to squint at my writing this time. Mine says 612. Is that what y'all get?
I don't know.
Or 613? Mine says 613. Now, you'll want to keep in mind what the 613 Kelvin's actually telling you. That means that if the reaction takes place at this temperature, G equals 0. But remember, in order to make it thermodynamically favored, G's got to be negative. So then what must be true? For it to be spontaneous, we need the reaction to take place at a temperature that is below 613. Because when it's 613, it's 0. So if this is any number lower than that, it'll make it negative. All right? Therefore, spontaneous.
Wait, so what would the answer be? Would it be like a number below 6?
Any number, yeah, less
Less
than
than.
613. All right, hey, there's one more slide. Actually, I have it here. You don't have to show it unless y'all want to see it. The very last slide that it's showing is very quick. It's just the connection between G and S. It gives you 3 reactions, and it asks how to tell what the sign of G would be. But really, that's super simple because you already know how to look at a reaction and know what the sign of S is, right? Like if it forms a solid, the sign of S is negative. If it forms a gas, the sign of S is positive, right? So we've already learned how to do that in this lecture. But what we know is that whatever the sign of S is, the sign of G is the opposite, all right? So in the first example, if you're looking at your slides, it forms a solid which makes S negative, all right? If S is negative and it wants to know what G is, we just know that G is positive, all right? Both of which support the fact that it's not spontaneous, all right? The second one on your slide is one that we did earlier in lecture. It's the breaking of bonds, which, as we already said, makes S positive. That makes G negative, therefore thermodynamically favored. And then lastly, it starts with gases and liquids, and it goes to gases only. That's good for entropy. S goes up, G's negative. We are spontaneous.
This one we're very spontaneous.
Wait, can you repeat that?
Yeah.
For which? For which part? C?
The C, yeah.
For C, it's the same thing. We're going towards the gaseous form. Going towards the gaseous form always makes entropy positive. All right, so if entropy is positive, Gibbs free energy is going to immediately be negative.
And A is negative?
Right. No, yeah, well, A is the opposite. It depends on what you're talking about.
I'm talking about
For A on there is going to have your entropy be negative. It's going to make Gibbs free energy be positive, neither of which favor it thermodynamically. Because they always go opposite directions, right? And for it to be spontaneous, S has to be positive and G has to be negative.
But I'm saying like S is negative on A, right?